Hello, everyone, and welcome to today's webinar. We're allowing a couple of minutes for everyone to join, and we'll get started shortly. Thanks for your patience. Hello, everyone. If you're just joining us now, we're giving everyone just a moment to join. I see that we still have quite a few people in the queue joining, so we're going to give them just a moment. Thank you so much for your patience. All right, everyone. Thank you for joining today. I'm Robin Carr, and I'll be your moderator for today's event. Thanks for being here. Before we get started, I have a few housekeeping items to go over. If you lose audio or video, simply exit GoToWebinar and come back to reset your connection. The chat feature is available in your GoToWebinar menu, and that's really meant just for general comments or if you need to request any technical assistance. You can ask questions using the questions feature available in your GoToWebinar menu, and we'll get to as many questions as we can at the end of the presentation. The handout section of your GoToWebinar menu includes a handout of today's presentation, 2 slides to a page, so you're welcome to download that at any time during today's presentation. Additionally, the presentation is being recorded. It'll be available on the Fluke YouTube channel in the next couple business days. So we'll hear our speaker, Stephen Hudson, and then we'll go into our Q&A session and answer as many questions as we possibly can. So Stephen is Stephen is Director of Professional Services at Fluke Reliability. With over 30 years of vibration analysis, expertise, business development, product and service delivery, and scalable operations, he focuses on efficiency and promoting internal collaboration for consistent results, client partnership, and brand quality. All right, everyone, you're here today for wireless sensor, MEMS, accelerometer basics. Stephen, take it away.
Hi, everybody. Good morning, good evening. Thanks, Robin. Appreciate it. So today we're going to talk a little bit about MEMS accelerometer, something that I think many of us know a little bit about, a few of us know a lot about. They're fairly new, at least over the past decade or so, to the vibration world. So we're just going to kind of talk a little bit today and see if we can, work together to kind of learn more about these sensors. A little bit about myself. Robin already did a really great introduction. So I've been with Azima DLI, now Fluke, for almost 15 years now. I manage the professional services group, basically Watchman Reliability brand. And so all the services people that do analysis on this side roll up to me. And we've got a really great group. I've been doing predictive maintenance about 35 years. I'm a Cat IV Vibration Analyst, and I have a background in Navy nuclear power, for those of you that don't know much about me. Talking a little bit about accelerometers, again, today's main topic is going to be MEMS sensors, but we're going to start a little bit about talking about more of the traditional accelerometers that we're all kind of used to. So just hopefully I can teach you guys a little something today, a little bit more about what I know or don't know about MEMS sensors. So we'll start with just kind of a general comparison between piezoelectric accelerometers, which are kind of the standard that we've used for the last 50 years in the vibration analysis world and much of the other. Piezoelectric accelerometers, their advantages, they got great high frequency response. They've got really, wide dynamic range, amplitude range, and they're a very flexible platform. We can use them for both our portable data collector and our online systems, as do most They're readily available in the industry. You can go out to many of the vendors that directly sell these and get several different kinds of accelerometers to suit your needs. Whereas MEMS accelerometers, they're fairly new to the market, although we see them every day in our life. I'll talk about that in a second. But they're very low cost. They have great low frequency response, and they're a relatively simple platform to work with, certainly for digital designers. Back to our legacy system, you know, this is traditionally, this is a picture, for example, of our Trio devices, and you know, just showing here that we use a piezo electric accelerometer, triaxial, pretty standard again in the industry. I think we were the first in the industry to use triaxial. Many are jumping on board with that in the recent decades. But you know, what is piezoelectricity? How does this sensor work? Piezoelectricity is basically the ability of a crystalline material to develop an electrical charge in response to applied mechanical stress, and vice versa. Piezoelectric devices are both used for accelerometers, things that we use to measure, which would be on the left here, and also on the right here. Some of the guitar pickups use piezoelectric sensors to basically pick up you know, those vibrations, transmit them into an amplifier, and then it can be used vice versa, such as maybe the thing that vibrates your cell phone is a piezoelectric device, and or your typical charcoal igniter. When you snap that switch and it gives you a little spark, you're basically striking a piezoelectric crystal that gives you that voltage. So obviously that effect that happens within a crystal is very useful to us in these devices. A piezoelectric accelerometer, just going to talk basically about what I would call our benchmark technology here that we've used for decades in the vibration world. You know, the pros of these devices, they have a very high dynamic range, almost matched by nothing that I'm aware of, in the ability to measure amplitudes at both a very, very low amplitude and very, very high amplitude, oftentimes in the same device. They also have a very wide frequency range. And again, we're going to dive in a little bit on the frequency range of these devices. Cons, they do require typically a unique power supply. They're not 4 to 20 milliamp. They're not a standard voltage supply. They almost always have some sort of specialized power supply. There are different versions of these sensors and different versions of the power supplies, but generally they're designed to drive a two-wire device as simply as possible and maintain that high dynamic range. And also they require separate signal processing. These are analog devices. They just basically give you a voltage, a varying voltage or varying current output based upon the amplification that's done within the sensor, and they require a separate analog to digital converter. So an ADC here is what I refer to, and keeping in mind that they have a very low output at low frequency. That has to do with the nature of how they measure. The other thing I want to note here is we'll talk a little bit more about how this works, but here you see a typical accelerometer with the crystal and the white, and then the proof mass, the cutaway here showing the mass that surrounds that shear mode crystalline device. And then interestingly enough, within this stainless steel package that you get your sensor in, there's also an amplifier. That's not always the case, but in most, again, today's traditional accelerometers, it allows you to have, once that amplifier's inside, you can have cable lengths from 10 foot all the way to maybe 500 foot without any significant degradation in signal. That's the advantage of having these style of accelerometers. So talking a little bit about their function, and that piezoelectric effect of the crystalline is something that gives you a proportionality between the voltage output. Again, these do output in voltage mode, and again, most of them do have some sort of amplifier built into the package, but it gives you a voltage proportional to force. And then it's pretty much a simple calculation of force equal mass times acceleration. And in this case, we have a known seismic mass in those accelerometers. That combined with whatever amplification that internal electronics gives you the calibrated output of that device. Excuse me. I'm showing here shear mode, but there are shear mode and compression mode type accelerometers. And again, the shear mode is shown, which is again a ring within a ring. I'm showing here a crystalline ring in the kind of light green, and then the seismic mass is mounted to the outside of that. There's no moving parts here. The entire unit moves as a single unit, and that seismic mass, we're measuring the force that as the case vibrates, there's a force put into that seismic mass to try and accelerate it, and that crystal ring will measure that force and give you that direct force output. Again, the sensing element is rigid. And again, that's a charge signal. It's basically a high impedance signal that's proportional to force that's being measured between the casing base and the seismic mass. And then you've got that typically mounted at the top, some sort of electronic amplifier, gives you a low impedance voltage signals. And again, this is not the only style. This is ICP, which is pretty standard for our devices, but there are other types of amplifiers out there that serve different functions and have different advantages. But one of the things I just want to point out, again, if you can see the illustration, it's just showing the whole unit moves as a single unit, and again, there's no internal moving parts. Very rugged, very long-lasting, and again, lots of advantages and very high dynamic range typically. There can be some fragility in these at super high Gs. You can destroy the electronics. You can damage these if you drop an accelerometer, for example. They can be very expensive. I know that our Triax accelerometer is well over $1,000. So, you know, you tend to not want to drop these, but they are very robust in general terms. So, and again, that varying stress across that crystal gives you that varying charge, and you convert that to an analog voltage in the amplifier in the case of these style of accelerometers. And it does require external signal processing and digitization. So a little bit more about that. Typical setup for, again, a legacy accelerometer would be that you, and this one shows more of a compression mode type accelerometer, but that voltage, whatever that power supply exists, and in our case, it exists in our DP unit, which is part of our analyzer. So all of this circuitry resides within our analyzer, including a power supply, a very specialized power supply, anti-aliasing. Again, I talk in my other series about meeting Nyquist criteria. We got to make sure that signal meets Nyquist criteria before we convert it into a digital signal. And then from there, we can create our FFTs, our time series data, and we can have a digital output to whatever analyzer or whatever database this data is going to. One of the most important things to note about a piezoelectric sensor is that it has kind of a common frequency response, and it will vary significantly from sensor to sensor what the high range and the low range is, but the general shape remains somewhat the same, which is they typically respond poorly in the very low frequency, keeping in mind that this is a logarithmic scale. So here we're looking at 0 to 10 hertz. There's typically some sort of roll off in the low frequency. And again, because it measures acceleration directly, that combined with the fact that it cannot go to DC, these devices have a certain roll off. And you can control this frequency response by both the size of the seismic mass, and you can manipulate the amplifier somewhat internal to it. There is an RC time constant that can be manipulated to get improved low frequency, but you'll oftentimes suffer settling times and things like that in an accelerometer. The other kind of notable feature is some sort of mechanical resonance of the sensor on the high frequency end. Typically, you will get an increase or some sort of resonance peak out typically beyond the linear range where you're measuring, but it's notable that most sensors will have some sort of resonance frequency out there. And then finally, at the very high end, they will begin to dive off and be very non-responsive to super high frequencies. But again, this gives us, again, logarithmic scale. Some of these sensors can easily measure out beyond 50 kilohertz. So they're very capable, and keeping in mind, just because it's beyond the linear range doesn't mean your sensor won't pick up those frequencies. So if there's frequencies out there, if you have machines that are putting out very high frequencies, your sensor will be sensitive to it. In fact, somewhat highly sensitive to it. And so just be aware that if it's picking it up, it's coming down those wires. It's an analog device. So very useful sensors if they're applied correctly. So that's about all we're going to talk about on piezoelectric directly. Let's talk a little bit about our wireless devices and kind of why are we talking about our wireless sensors and MEMS, because our sensors in particular use MEMS accelerometer technology. Not all wireless sensors do, but most do, and we'll talk a little bit about why and what the advantages and disadvantages are. Our accelerometer, our wireless accelerometer does support our what we consider to be high enough resolution, high sampling rate, and it does do our impact DMOD. It supports frequent data collection, and it's got, this particular sensor has a non-replaceable battery that we give a 3-year guarantee to. It's easy to set up, easy to train. And we have various network options to get that data out to the cloud, because this only works with the cloud, and it's affordable to scale. So what is a MEMS accelerometer? That's kind of what this whole discussion has been about. MEMS stands for micro electromechanical system. It's a system in a package, meaning it's not an analog device. Everything is contained within this single chip, single tri-XXL with a digital output. I've kind of given an example here that there's basically 72 of these things would fit on a stamp. They're very small, and they're highly efficient in that way. This is an example of potentially circuitry that would be involved: a sensor, analog filters, analog digital converters, digital filters again, and logic, and basically give you a direct digital output out of this device. It makes it very efficient when built into some sort of digital platform like a wireless sensor. So this is the heart of our wireless sensor. The pros: it's compact, it's low power, low cost. They're DC coupled. We'll kind of circle back to that. The cons are they do have limited bandwidth in the high frequency range, and they have oftentimes limited amplitude range. Because they don't have quite the depth of, or nearly the depth of dynamic range that a piezoelectric accelerometer does, not currently, not with our current technology, they oftentimes, again, get amplitude limited, and that's something everybody should consider. A typical piezoelectric accelerometer could measure up to maybe 200 Gs. Maybe the linear range is 100 to 150 Gs, whereas these devices are oftentimes limited to 32 Gs. But it really, they can give them higher limits, but then we suffer limited range and limited amplitude dynamic range. So it's the balance of where they're at today. Now, what exactly is a MEMS sensor? If we dive into the sensor itself, and we talk about the MEMS sensor, it is a variable capacitance of a moving proof mass. So as we get that varying capacitance, it's proportional to that variation in acceleration. You get it. Here we're looking at basically a microscopic view of an example of one of these sensors, and there are different kinds. We're looking here at a comb type filter, a comb type accelerometer. I think they're most common, or certainly what we use, where we get these kind of comb fingers, which is illustrated over here on the left. But in the microscopic view, you can see that those are actually floating, moving fingers, and there is basically a micro mechanical spring on both ends of that proof mass, just like is illustrated over here on the left. It's supported. And again, here we're just looking at a single axis of a triax. So there are 3 individual sensors that are built into these chips. The displacement of that proof mass varies that capacitance as that moves. And so let's just illustrate this on the right here, where we're moving the proof mass. You can see that the distance between the comb fingers varies, and that gives us a varied capacitance output, directly measuring more or less the position of that proof mass. So we get kind of a displacement of the proof mass, giving you a varied capacitance, and that we can then relate to acceleration. So again, measuring very differently than a piezoelectric accelerometer, and the fact that it is the movement of the proof mass that gives you this acceleration output also means that we can see a direct measure of DC. Most of your cell phones will use this style of accelerometer to measure the movement of your phone. Everybody's used to that. They're very low resolution compared to what we use in this industry, but nonetheless, they have some of the same characteristics, but keeping in mind that you can measure actual gravity. In other words, this sensor can be aware of which of the 3 accelerometers is pointing in the direction of gravity and measure gravity because of that. That's what gives these that characteristic low frequency response that everybody talks about. So that's the big advantage of these sensors. Talking about the performance of this accelerometer now, again, this is the filter chain all built into the sensor itself, not any sort of external signal processing required. We get the MEMS sensor itself, we get the analog front end and analog to digital conversion. We get some low pass filtering. And again, this particular device is sampling at 26.7 kilohertz. It is a high resolution sensor. And then we get a composite output filter that allows us to decimate as needed for any additional output frequencies that we're after. Frequency response is very flat all the way from 0, and we'll compare the two here in just a minute, but it's flat all the way from 0 all the way out to about 7 kilohertz, and then begins to drop off out around 10 kilohertz, and then down. One of the things to note here is we don't get that typical resonance frequency that we see in piezoelectric accelerometers. But the other thing to notice is this is a very much narrower frequency band than you would see with a typical piezoelectric accelerometer as well. However, again, the advantage is in the low frequency. So restrictions in the high frequency range, but big advantages in the low frequency range. So back to kind of our initial slide, which is comparing piezoelectric to MEMS, and now some of the things that I've said, I hope will begin to make sense. Basically, with the piezoelectric, we get really good high frequency, really good amplitude range, a very flexible platform, whereas a MEMS sensor is low cost, low frequency, and a very simple platform. One of the most important things here that I want to discuss is that frequency range. And so that people understand that, again, they're 2 very different mechanical packages, and they operate in a different way, and we get a lot of overlap between them. But talking about where that overlap ends will give us some of the conversation about applicability. Where is one applicable versus the other type of sensor? So what we would call the linear range for a piezoelectric might be from 10 hertz all the way to maybe 15 kilohertz or 20 kilohertz, depending on the sensor that's chosen. You get a very wide linear range, but it does limit at the low frequency range. A MEMS sensor, on the other hand, will react linearly all the way from 0 to maybe, in our case, linear up to 7,000, good response up to 10,000 hertz, but nothing really beyond that that's measurable. Why is that important? Well, because I kind of split vibration analysis into 2 different categories as far as the actual raw data that's coming in. 0 to maybe 500 hertz or a little over 500 hertz is typically going to give you what we call machine motion faults, things like imbalance, alignment, sometimes looseness. Whereas impacting type faults are much higher in the frequency range, and they give you other kind of faults, such as early stage bearing faults, gear tooth faults, things that give you profile faults, things that give you kind of high frequency noise, raised noise floor. And all of those together are used by an average vibration analyst to give you a comprehensive understanding of what's going on in a machine. We kind of need both. Low resolution sensors many that are on the market today can give you many of the machine motion faults. But particularly when it comes to bearing, gear, and other kinds of very highly critical faults in a machine, you only get notification of those very late stage in that fault. So we tend to call them hand raisers, these kind of low resolution sensors. They're not early indicators, they're just simply late stage indicators when there's actual condition issues going on with a machine, whereas we are all accustomed to being able to measure and be somewhat more predictive, and so we need that high frequency range in order to get that predictability. So we didn't get on with some of the very early wireless sensors that were available 10 years ago, for example, that had these kind of low resolution approaches to the faults. So we think it's very important to capture both as much as we can in the high frequency range as well as in the low frequency range in order to basically diagnose between machine motion faults as well as more early stage and or severe style of faults coming in gearboxes. Excuse me. Allergies. So low speed wireless sensors. I've mentioned to you, let me just go back one, please. I've mentioned to you in the blue line here that we get very excellent low frequency response out of a MEMS sensor. But then we limit our current sensor as a deliverable to only shafts above 600 RPM. And I oftentimes get that question, why do you limit your sensor to 600 RPM if your MEMS sensor goes all the way to 0? Well, the simple answer is battery life, of course. The MEMS sensor is quite capable of the low frequency measurement, but the entire package, the wireless package, you have to consider that package and you have to consider battery life. When we measure low frequencies, when we use our online system, for example, to try and measure down to very low frequencies, we need a lot of time to do that. We need sometimes minutes worth of data. And in that wireless sensor, you have to stream that high resolution, high frequency data for not just a few seconds, but now minutes into some sort of buffer, post-process it, hold on to that data, and then be able to package it up and transfer it over some sort of wireless device. Again, something that would normally take a few seconds now takes into the minutes, and battery life suffers significantly. I'm going to give an example data set here. Best practice typically, what we try and achieve is 15 revolutions on any given shaft as a thumb rule, and with 4 averages and 50% overlap. With that said, on a 600 RPM example, one test would take 4¼ seconds to sample that data and produce about 113,000 samples. And with that, we can give a 3-year battery life if we sample at that rate. A 12 RPM example is going to be, one test is going to take 188 seconds, so several minutes, and it's going to produce almost 5 million samples. And calculation on that gives us a battery life of about 45 days. So you can see, particularly with a wireless sensor that is a non-replaceable battery, how this doesn't really work for us. That said, we are developing some additional low frequency capability into this sensor that should be soon to come. We can talk more on that later. So kind of to wrap up where this sits in our profiles, right? We have our Trio device on the left, an online device in the middle. They're both capable of sampling at 40 kilohertz, very high sample run, very high bandwidth, excuse me, sampling at 102 kilohertz. They're meant to support these piezoelectric sensors that have capability out in that range, as well as they can sample. Our online system, for example, can monitor down to 5 RPM because it can sample and buffer, you know, several million samples. It looks like 14 million samples on this particular device, do our impact testing and things like that. Whereas our wireless accelerometer certainly samples fast enough for impacting, 26.7 kilohertz, but it has a dynamic range of plus or minus 16 Gs and 1600 lines of resolution and 3-year battery life. So it certainly has to fit within some guardrails when we look at an application. So typically when a site, you know, is interested in these kind of sensors, we will go do some sort of walk down and verify the machine types are a good fit for the wireless sensor. And if they're not, we may recommend using a Trio, a walk around device, or sometimes even an online device. This table was put together to kind of showcase the differences between different kind of accelerometers. On the left here is the 1 kilohertz, 2 kilohertz sensors, many of which are out there. They're the same kind of sensors that we see in our cell phones, but many have been applied to vibration sensors as well. They certainly have their limitations, as I mentioned, for machine motion kind of faults, soft foot imbalance, angular parallel alignment issues, and work okay in that, but then they get very limited in what they can see for bearing faults, gear faults, load faults, you know, compressor faults, things like that. And then even in some cases, when we get into some of the high speed or very low speed machines, we limit our applications to our Trio or our Sprite. Although, as I mentioned, we are working currently on development of low speed capabilities that will bring some of these other low speed machines up into the applicability of our wireless, which is the one right in the middle, which again gives us most all of the faults that we're after, and we find it to be work very well with our automated diagnostic system. Let's talk a little bit about impacting. I've kind of mentioned it, and we talked a little bit about the frequency range of the two different sensor types, and that basically off here on the right-hand side of our frequency range, you know, where we're getting between, you know, maybe 1,000 and 50,000 hertz, where we particularly can measure impact faults. Again, I oftentimes equate this to ultrasound. People ask me about this all the time. Yes, these sensors are capable of measuring in that ultrasound range, which is that frequency range. And oftentimes, if you're using this kind of impact detection, that's kind of belt and suspenders with UE. And this is really where we get those early stage faults, but also with the way it's measured here, that does track into late stage faults as well. So very useful to measure impacting in these high frequency ranges. We do it natively now with our analyzers and have for the past decade. And so again, we kind of waited in the market until we got high enough resolution sensors that we could get an overlap up here. And we feel like we have a very good overlap with these particular sensors, but they react differently. And I just want to point that out to everybody that the piezoelectric still has a higher frequency range. So there are certain fault types that will be seen that are sometimes a little bit beyond the range of the current MEMS sensors. And so we certainly do our best to measure that in our programs. So, you know, as an example now, we kind of have a narrower impacting fault range that we can measure. That doesn't mean we're blind to it. What we typically have experienced, and we don't get a lot of examples of this because basically the only way we can really measure this is if we have both a piezoelectric sensor and a MEMS sensor on the same machine, and it happens to be in fault, and we capture this kind of fault. So we have a few cases where this has happened. And what we what we theorized and what seems to hold true is that the MEMS sensor is just less sensitive to these kind of faults. So we see lower amplitude, we see lower impacting amplitude. We may see 30 Gs with a piezoelectric sensor, and we may see 15 Gs with a MEMS sensor. So we do expect that. We feel that we compensate for that because we use location-specific statistical alarming. So the alarm set point for a piezoelectric-based impact detection is going to be different than the alarm set point for a MEMS-based, and they're going to be based upon that individual location and the history of the impacting coming from that specific machine location on that specific machine. So we've had very good luck, and I'll show you a case in just a minute here where we captured a mid-stage bearing fault with a MEMS sensor, and we validated that it is in fact capable of detecting those impacting. So a little bit about how we do this. This came from our engineering team. Basically our impact algorithm is embedded into the firmware, and we capture that raw acceleration waveform. In fact, we capture about 0.77 seconds. And that gives us 20,480 raw samples. So we get a time waveform of that resolution. We put that into a memory buffer because, again, remember, this is all digital at this point. We 2,000 hertz high pass that so that we remove all the machine motion. And then we decimate that at 10 samples per sample to give us a 2048 reduced sample time waveform. And then from that, we do two things. One, every hour, we just simply capture that max value, that single integer value off of that impact time data, and we transmit that over the air back to be tracked as an hourly measurement along with the overall vibration and the temperature. So that's being sent back every hour. And then once a day when we capture our normal spectrums, and we also capture this impact DMOD time waveform, and we transmit that over the air. Again, I have a separate webinar on impact DMOD and the fact that it's more or less just a data compression methodology that maintains the maximum values in that time data. So, and again, I mentioned before, we statistically alert that based on sensor specific data. So, so we're finding this to be very useful in tracking when we see those kind of impacting changes on machine bearings and machine gear trains, and, as an example. So this is just some example data where we have shown here, I think it is, I know you probably can't read it here, but it's about 16 Gs. No, it's going to be more than that. Well, I can't quite read the max value here, but it's around 20 Gs worth of impacting measured. And again, this is your 0.7 seconds worth of time data that's measured and transmitted through our wireless sensor of just raw high frequency data. And it does give us a diagnostic here of non-synchronous impacting. And in this case, it was a pump, and that bearing was in fact failing and was subsequently replaced. So I just wanted to give you that example. Well, this is gonna conclude my discussion about MEMS sensors. I think I've left us plenty of time for questions. So I will turn it back over to Robin to see if she can field any of those questions for us.
We do have some questions, Stephen. Let me expand this so I can make sure that I'm getting them in the right order. Let's see. All right. The limitation on ICP would be temperature range and high frequency as per my experience. Is that correct?
Temperature range on an ICP is typically limited by the electronics that are inside. If you recall, I said that you got a stainless steel package there, but there's still electronics inside of it. So typical, you can think of solder melting. from a very simplistic standpoint, but typically they're going to be below 250-degree application. That said, that's not really a limitation of IC. It is a limitation of ICP, but not of piezoelectric. You can get high temperature piezoelectrics. One of the ways you do that is by removing that amplifier from inside of the piezoelectric sensor and putting it remotely. Those are charge mode accelerometers, so we can get into some pretty high temperatures with piezoelectric accelerometers, and that's when we get into hot oil pumps and things like that. That's oftentimes the approach we have to take. So, can you read back what the other limitation he had mentioned there, or they had mentioned there?
Let's see. Let me find that one again. Pardon me. The limitation on ICP would be temperature range and high frequency, as per my experience. Is that correct?
Yes, sorry about forgetting the second part of that question. High frequency is in fact the limitation, but again, it's nowhere near as restricting as a MEMS sensor. Our high frequency range, typically that's given by an accelerometer manufacturer, is going to be where they measure the roll off or the increase, or as that sensor heads towards its resonance peak, where it falls outside of the linear range. And again, they can craft that sensor to higher frequencies by reducing the seismic mass, increasing that high frequency resonance of that sensor. So you can get sensors that are very specifically crafted to go to very high frequencies. But again, a general accelerometer, those are the limits. Thank you.
Thank you. All right, Stephen, let's see. The next one I have. Would a wireless sensor be a good application for a conveyor?
All right, that's an interesting question. Yes, sometimes. The answer is sometimes. When we look at conveyors, one of the things we look at is there are many different types of conveyors, and there's many different speed outputs. Sometimes that speed output falls into a low frequency range. That doesn't mean that the drive unit isn't a good application. Oftentimes the motor and the gearbox have many or all the shafts that are above 600 RPM. Again, as I mentioned, we have a lower frequency version of this sensor coming, so tune in soon to be able to be. We're pulling many of those machines up into our application list as we speak. But again, one of the things I might avoid would be head shafts and tail shafts on conveyors if they're below 600 RPM, and most are. And again, maybe that would be an online system currently, or again, as we get better resolution and into that low frequency range, they will become a better application for our wireless sensor. Yes, thank you.
Thank you. And then how do MEMS sensors work in an enclosed environment inside a gearbox?
I can't say that we have used that application inside of a gearbox. It seems as though it would be plausible, not with our wireless sensor package. We wouldn't want to put our wireless sensor package inside of a gearbox. Survivability, oil temperatures, things like that. It's just, while it is designed to be capable of weather, it is not tested in those environments. The use of a MEMS sensor, we don't currently have a MEMS sensor package that is packaged like an ICP accelerometer, but it is plausible. I have heard of these sensor types. My experience with inside of gearboxes has again been primarily piezoelectric sensors that are built for that survivability in those environments, and certainly can give us the signal we need. But as far as applicability, it's just going to really boil down to what kind of packaging that particular MEMS sensor is put into, and if it's industrialized enough to be robust to handle both temperatures as well as probably integral cable, those kind of things, and then have some sort of external ability to pick up that digital signal and transmit it back to some sort of database.
And then are MEMS sensors usable for variable speed applications?
That's a good question. Ours are, yes, and and really that boils down more to a software question than a hardware question. And so for our particular software, since it's diagnostic in nature, we have to know the machine speed in order for our diagnostics to be accurate, right? Typically for manual analysts, they're going in there, they're verifying the machine running speed in the data. They're using their own pattern recognition to do that. With our system, with our expert diagnostic system, we have really crafted our speed normalization routines to be able to find a wide speed variation on a variable speed machine. So, and I'm going to define this a little bit further, but we typically, once we set up a wireless sensor on a machine, can see as much as 30% machine speed variation and still capture that speed strictly from pattern recognition. So looking strictly at the spectrum and verifying that the speed has changed of the machine and renormalizing to that new machine speed so that we can give a proper diagnostic output. And the other part of that answer is there are certain machines that do vary speed that are not a good application, and those I would call constantly changing speed. Things like downcoilers and unwinders in paper factories and things like that, where the machine speed is changing all the time. So when I say it's capable of variable speed machines, that supposes that the machine speed will be at least constant or relatively constant throughout the sample period of time, which is just a few seconds, once a day. As long as it can find and maintain that constant speed during that sample time, then that data will be acceptable and will be accepted well by our system and speed normalized correctly. But if it's constantly varying speed and we can't find a time during the day where it's at one speed, that does become a difficult application. Thank you.
All right, well, I have lots of questions for you, so we'll keep going. Conveyor gearbox, which is having 3 shafts. Do we need to install wireless sensors on all the shafts, DE and NDE?
That's a good question. This really goes back to the history of DLI back into the 60s. It started using triax accelerometers in the 80s. A lot of experience with triax, and we kind of evolved over time to use something we call the 24-inch rule. I think it's a 60-centimeter rule, where a sensor can generally detect any shafts that are within a 24-inch radius on a casing like a gearbox casing. So we try not to over-apply, particularly because triax sensors can be very expensive. So there has to be some economy at scale here. So we generally approach this where we apply one sensor for every 24 inches. And on a conveyor gearbox, for example, that may result in a single or maybe a maximum of 2 sensors, even though there's 3 shafts, because we use those intermediate sensors to capture more than just one shaft. Again, the data is going to be, all the machine motion data is going to be the same across that gearbox. It's just going to be your high frequency data. And we know, we've learned over time that the high frequency data transmits very well even in a 24-inch path. So that's typically the thumb rule we use. So you'll see oftentimes with smaller conveyors, there may just be one sensor, one triax sensor, be it a wireless or be it a wired triax location on either side of that gearbox. So we capture both bearing sets. As they get into larger gearbox, there may be 2 sensors, and there may, on very large gearbox, there can be more than 3. Certainly, when we get into the truck size gearboxes, we'll have multiple locations across those gearboxes. But in small conveyor gearboxes, we typically try and put one sensor within that 24-inch radius that we typically have found works very well. And our diagnostic system, the configuration of that gearbox is built in the diagnostic system such that we can then define between those different shaft bearing faults as necessary. Thank you.
Excellent. I have another gearbox question.
Good.
What about using them on cooling tower gearboxes? So can we do away with the wires and do away with manual data collection on the gearboxes?
That's our intent. Yes, we have a couple applications where we do have these in cooling towers. They survive very well. They're very well suited and very well rated for cooling tower gearboxes. Our limit so far has been that 600 RPM limit, but again, we're moving away from that very soon. And again, like mentioned before, what this means when we limit it to 600 RPM, it just is us saying we can't easily resolve frequencies below 600 RPM, but we will always be able to resolve gear mesh frequencies, bearing tones, things that are oftentimes important in those usually right angle gearboxes and oftentimes multi-stage gearboxes that are in a cooling tower. So I'm gonna say yes, a cooling tower is a good application for wireless sensors, and we're getting better at it as we speak. So thank you for that.
All right, we have about 10 minutes left, and I definitely have 10 minutes worth of questions for you.
All right.
Let's see, I have 3 questions and I'll ask them separately, but all deal with FFT.
Okay.
The first one is MIMS calculates FFT to develop the spectra, but how are common machine faults diagnostics reported for non-vibration experts like the legacy Fluke 810?
I don't know if I can give a good comparison to the legacy 810, but I will say this, yes, the FFTs are what are forwarded. This really gets more into our diagnostic approach, which is we have diagnostic software, and again, I think it is kind of baked in, a version of that software is kind of baked into the 810. And but for us, we always approach that with a belt and suspenders, meaning you get not just the vibration diagnostic software. And again, that software analyzes that spectral data. It basically compares a statistically averaged spectrum to the incoming data. It pulls out exceptions, it pulls out features, and it pulls out exceedances, and it passes that to a diagnostic system, which is built to understand that particular machine. Somebody gave a cooling tower, it will know that there's a motor, that there's a shaft, that there's a gearbox. It will potentially know the shaft speeds of each shaft within that gearbox, and it will be able to point towards the specific part of that machine that is in fault and give you that diagnostic. So the belt and suspenders approach that we take is that any fault that becomes serious, actionable fault gets pushed to a human analyst. So one of my analyst team then reviews that, validates those results, because again, this may end up being a costly repair for you, the customer. And so we want to confirm those results, add any additional context that the human analyst might have. Analysts are very experienced and they understand a lot of the nuance here, particularly in certain industries such as food or metals, and then pass that result to you, the customer. So really, compared to that other approach, it just adds a lot of additional context. Plus, in this case, the most important piece is that we are upfront during the startup phase of a program. We're adding very detailed machine information as opposed to some of the approaches that just add a very generic. That may work very well for a pump motor combination, but it may not, again, work so well for a gearbox. If the diagnostic system doesn't understand your machine, it's going to give you very generic results and not very specific results. So our approach today is to be as specific as possible, and we do that by learning as much as we can upfront about your machines and continuing to evolve that process as we go, meaning as we find out more about the machine, or if we find out bearing information, all of that plays into the ultimate result that you get to help you make those ultimate maintenance decisions in your repair schedule. Thanks.
Okay, and I was incorrect. It was the same question that just got entered 3 times. So we
Okay.
still have plenty of other questions though. All right, next one. Say for 10 meters distance from a target, do wired and wireless sensors give the same accuracy in general for rotating machinery, such as a motor, to study the health of the motor?
I am not sure if I understand the question, just to be honest. I don't know if you can give any additional clarification, because you mentioned 10 meters from a motor.
Yeah.
And that part only makes sense with a wired sensor, right? If you're wired and your wiring runs 10 meters away, and you're picking that up with some device. This may tie into that previous cooling tower question, where cooling towers are inaccessible, and oftentimes you will be 10 meters away from that motor. The wireless device in this case would still have to be mounted directly on that machine. In the case of a cooling tower, obviously during the setup that would have to be locked out, put in a safe condition, the sensors would have to be mounted, and then that data would be transmitted hourly and daily out to a gateway, which would then go to the cloud. Whereas wired accelerometers are typically, in those same scenarios, are attached to the machine, again, during a lockout, tagout period. Cables are cabled out to the outside of the machine to some sort of junction box, and then a portable device is plugged in, or an online device is permanently connected. Those are the scenarios in which I understand the question. And again, they both have their advantages and disadvantages. You know, there's a big cost advantage of wireless over wired systems. Trio walk-around systems are still the least expensive altogether, but wireless over wired online systems is still quite a bit cheaper and gives us that hourly and daily data that gives us a lot of consistency around the results and understanding of the machine running, and when it's in fault, how that fault is progressing. I don't know if that answered your question, but that's to the best I understand your question. Thank you.
Okay, thank you. And for our participants, we have about 4 minutes left and more than 4 minutes of questions, but I'll try to get to as many of them as I can. The next question, Stephen, is we have installed more than 100 ACCELL 310s here. Can we now undertake third-party sensors into our EA plus dashboard?
Okay, that's an interesting question. So it sounds like to me, let me see if I can restate this and hopefully I get it right. You've installed more than 100 of our sensors, the sensors that I gave examples of here, in your system. And you're wanting to know if you add a third-party sensor, if we'll be able to bring that in. The answer is maybe, possibly, and sometimes, depending on the sensor type, probably. We do strive to be data agnostic. I say that, I'll say straight up front, me and my team are data snobs. We like good data. So if you install third-party sensors, make sure they're very high quality. Two, they also have to be compatible. They have to be open source. We have APIs that allow us to ingest other people's data. We have done this. We've done this at scale. We have several large refineries that are using somebody else's sensor, and we're ingesting that data successfully into our diagnostic package. It doesn't give us all the ranges and features we always want, but usually we can make it work good enough. So again, not really interested in going to all of that cost and time for low resolution sensors, but if, again, there are high resolution sensors out there, and if they're open platform and we can access that data, we certainly are capable of ingesting it. There's a cost associated with doing that initially, but once that's done, then we can readily ingest that data. And again, we're getting, like I said, I've got a couple refineries, we're going to be getting almost 5,000 sensor tests a day from those, and running that through our diagnostic system. So it does come with some upfront refining. Basically, we have to build all those templates, we have to build all those baselines, and construct what we call MIDs, which are templates. Once that's done, then the system can be maintained with minimal effort and kind of have that high resolution diagnostic output. And in this case, those refineries have their own analysts, and they do the final review. They're the ones reviewing all of those signals. But again, 5,000 tests coming in a day. This is what people didn't really foresee with wireless sensors. Is it's a huge amount of data, and it's very hard to screen that data without a good diagnostic system. And that's the advantage of doing what you've suggested. Thank you.
I think I have 2 quick questions I can squeeze in.
Okay.
The first one is, can this equipment be used in oil immersed pumps?
Potentially. I don't know that the sensor could be immersed in oil, so it depends on what kind of oil immersed pump you're talking about. I'm trying to think of an application. I really can't. Oftentimes, when they're oil immersed, if they're a vertical pump, sometimes we can get a sensor at the upper bearing, but oftentimes not down in the oil bath. That is not going to transmit out. That would have to be piezoelectric application. Go ahead.
And my last quick question, do MEMS support Bluetooth and cellular applications?
That's a good question. Our MEMS sensors don't support Bluetooth. We use a wire pass radio, which is a mesh network. We find it to be very robust, and our gateways do support cellular or network connections. So we can go back through the internet via wired connection, a wireless internet connection, or a cellular gateway connection. So getting the data to the cloud, that's the first piece. Again, Bluetooth would typically be, there are sensors out there that are Bluetooth. We use a different radio. Again, that's wire pass. And one of the biggest advantages is we find it to be very much more robust. I often tell the story of my team doing a setup, and they finished the setup and they had an extra sensor that was reporting in, and they didn't know where it was. Come to find out, it was in the trunk of somebody's car that they had forgotten left on, and even out in the parking lot in the trunk of a car, that sensor found a way to communicate with the rest of the sensors and get its signal back to the gateway. So again, we find WirePass to be an exceptional platform for us to use for these wireless sensors. Thank you.
That's pretty impressive. Well, thank you, Stephen, for an amazing presentation, always so very informative. And to our audience, thank you for joining us today. As a quick FYI, when you exit GoToWebinar, there will be a window that pops up with a very short 30-second survey. We appreciate your feedback so you can help us to continue to offer this great content. Thank you for joining today, and have a great day, everyone. Thank you, Stephen.
Thank you, everybody. Appreciate you sticking around.